Very happy caucus day. I know that I've said it a few times, and I'm going to say it again. If you are going to be 18 by November 3rd, you have the opportunity to participate in the First in the Nation caucuses. It is so great, right? You do not have to be registered already. You can register to vote on site. So you just go there with an ID so they can, know who you are and all that sort of stuff, and you can register, okay? If you are planning to participate either as an observer or as a caucus attendee, somebody who is going to be counted, okay, make sure that you arrive by 7 o'clock, okay? If you are hoping to participate in the alignment process, if you get there after 7 o'clock, they'll say, sorry, you can't do that, right? So even if you're not checked in by 7, as long as you're in line by 7 o'clock, that is the cutoff time. Anyone can be an observer. So even if you're not going to be 18 by November 3rd, you can still go and observe and watch history happen, right? Okay. So I want to strongly encourage you guys to go and give it a shot and have a good time with it. I talked to one of my former students who came in at lunch and she was like, I'm super nervous and I don't know what it's gonna be like. And we talked it through and it's great and she's gonna be fine, right? There are tons of people that will be there, okay? Lots of other people that don't know what's going on either, so it's totally fine. There are people there to help you. So anyway, I would very much recommend, I strongly recommend that you go and give it a shot. Democrat, Republican, doesn't matter. Everybody caucuses, right? It's everybody's involved. All right. Do you have any questions about caucuses before we move on? I feel very strongly. I'm going to be really tired tomorrow. That's okay. Okay. All right. So let me tell you my plan for the day, the week, etc. We're going to do a warm-up problem. We're going to finish up, or not finish up, but formalize Newton's first law, which we spent some time with in that we were talking about equilibrium last week. Thursday, we did a lab. For those of you that were here Friday, we did a bunch of kind of analysis of that lab stuff. We'll talk it through today, okay? And then we're going to add in some more things. We'll go through at about 10 minutes before the end. Eden's going to let me know that it is time, and then I will give you your Unit 6 test back. Are you on that? Is that okay? Fantastic. All right. In terms of our plans for the week, today and tomorrow, we're going to be doing problem solving, okay? Wednesday, we've got an applied problem. So those are kind of you remember we did the ballistic pendulum problem. We've done others kind of throughout the year where it's a lab, but really there's a problem associated with it that we'll turn in. So we will be thinking kind of clearly through that. And that will kind of move us through. I do want to show you where we're at kind of on our calendar. I had mentioned to you that we may have a kind of a quiz partway through the unit and then a test at the end, just because I feel like it will be better than trying to split this up into 2 distinct units for everybody involved. So we are right here on Monday. I am thinking that we will be ready for some sort of assessment here between this day and this day. So I'm open to you telling me when that would be. I don't think it'll be a whole period. It would just be a couple of questions or something like that. So we could either do it on Friday, we could do it on Monday. I don't want to push it too late because then it's just going to be going further down. So think about kind of what the rest of your late week, early next week is going to look like, and then we'll touch base about that later this week. Does that sound okay? Unless there's anybody that has strong feelings right now. Okay, so maybe not on Friday. Good to know. So maybe Monday or Tuesday. Okay. Well, I mean, that is a non-zero amount. Yeah. On Friday as well. So maybe Friday is not the best day for us to take our quiz. Is that fair to say? Okay, so maybe we'll do it Monday or Tuesday. And whatever we do on Friday, which it looks like it's just going to be some problem solving, either it will be recorded or it will be able to be handed out to you. And knowing that, I will try and get that to you ahead of time. Sound good to everybody? Okay. All right. So whether you were here on Friday or not, I think that you all have the ability to approach this warm-up problem. So get out some paper. You're going to definitely need to have paper today to write down stuff. So then take a look at this problem. Read it through, discuss it. I'll give you just a couple minutes to take a look, and then we will discuss it. That's what I was hoping. All right. So one of the things that I like about this unit and this problem in particular is that you don't have to understand a lot of physics to get this, right? In fact, when I was in my daughter's classroom last fall, and we were like doing like a tour of the classroom, they have something like this set up for them to learn about balance, okay? And I don't think it had keys. It probably had some sort of cute little colorful blocks or something to hang. But you may have encountered something like this before. Now, I don't need you to know exactly what's going to happen, but I just want you to give me a gut feeling. What do you think might happen? So either it's going to sit still, it's going to fall this way, or it's going to fall this way, right? Like one's going to go up, one's going to go down. And while we're here, let's go ahead and decide what's what way. Can we do that real quick? So maybe on your paper, let's describe that. Chris, you want to say something. What is it that you want to say? Yeah, so let's talk about what that means. So just to make sure that everybody's on the same page, because I assume that y'all know how to read a clock, but maybe that's not true. I just want to make sure we're okay. So if you go up this way, is that the way that the hands on a clock would go? It is not. That is going to be counterclockwise. And we're going to call counterclockwise in terms of rotation, we're actually going to call that positive. That's a positive rotation. Okay? And sometimes people get upset with that because it's counter, right? It's the wrong way. But the counter argument to that is that when you measure an angle, we generally measure coming back to the unit circle, right? We measure from here, and this is the positive direction. Okay, so that's why we've decided that it's going to be positive, and it's a arbitrary decision. Remember, way back when we were doing kinematics, and we decided that generally we're going to call right positive and left negative, and that's just generally how we're going to call it, kind of like we're generally going to call up positive and down negative. You can do it the other way, it doesn't matter, as long as you're consistent. I am going to strongly encourage you, so that we can have a common language, to call counterclockwise, that's this way, positive, and then the alternative would be clockwise, the way the hands go on a clock, okay? And that will be what we call negative, okay? So just to kind of set that expectation and that understanding, that if something is rotating clockwise, positive, counterclockwise is negative. So without telling me which way you think it's going to rotate, if it rotated this way, if the 5 centimeters, 3 keys came down, would that be clockwise or counterclockwise? That would be clockwise. So again, so we're just kind of making sure we're all on the same page here. This would be clockwise or negative. And if the 2 keys 6 centimeters away went down, that would be counterclockwise. The whole thing is rotating counterclockwise or in the positive direction. How are we doing? Are we okay so far? Okay, so no kind of weird stuff. We haven't answered the question. I just want to kind of, so we're all on the same page. All right, now we're going to answer the question. So I'm going to ask if it either stays still, moves counterclockwise or clockwise. You ready? Got that answer in your brain? All right, how many of you think it's going to stand still? Good job, team. All right, how many of you think it's going to go counterclockwise? How many of you think it's going to go clockwise? That's a lot of hands voting for clockwise. So, no, I'm not saying it's wrong. That's the one you're voting for, right? The one that I just highlighted a bunch? Yeah? Why? Yeah? That is some units of something. Okay, walk me backwards a little bit, Chris. Now, before we engage Chris in his ridiculous unit conversation, let's revisit what we did on Friday and on Thursday. On Thursday, most of you all were here. You had a meter stick, and you put it on the end of a marker, right? And then you put a mass over here and you hung it here. And then you put another mass over here and you hung it here. And you found all these things that balance, right? Now, on Friday, somebody that was here, can you explain to my friends that weren't here what you did? You took a bunch of data, right? Because we had the data from Thursday. What did you do with that data? You graphed it, right? They graphed it. Why did they graph it? Because I told them to. I said, here's the situation. I said, yesterday we did this. And then today I want you to take the data and your experiences with you to this balancing beans thing. It was really fun. Maybe someday we'll get them out and just play again. Okay? And graph the data to determine a relationship. So I had to kind of pull on that and tug on that a little bit. And I'm not going to spend a lot of time on that, except to do a big reveal. So Chris, you just seem like you want to share lots of things today. Can I? You've done enough? Okay, so you don't want to tell me what you graphed? I don't want to talk. Oh, okay, I'll talk. Yeah. You graphed a line with a slope of 1. And what did you do to graph a line with a slope of 1? Grams, centimeters. Gram meters? Okay, changing your story. Jeez. And before we go too far, that's not what you guys did, but you did something similar and it was okay. Yeah. So this was the grams and the meters here, right? So on one side, so the mass of this times the distance on one side. And for some reason, you decided to multiply those together. Why did you decide to multiply those together? Don't be too fancy. Because you didn't know that word before.
What was it you said? The influence on the rotation.
Yes.
Is.
And what did you find? Like you had to have some sort of gut feeling in terms of why you might do that. When I multiply the mass times the distance here, how did it compare to the product of the mass times the distance on the other side? They were the same. So the mass times the distance on this side with the light blue, and again, it was the product multiplying them together, happens to equal the mass times the distance over here for any setups. So again, remember, if you weren't here on Friday, but you were on Thursday, if you had a bigger mass and a littler mass, remember the bigger mass, you had to kind of move in a little bit, didn't you, in order to get them to balance? So the distance here would be smaller for that bigger mass. And it just so happens, and we found that when we graph those on the X and Y axis, those two products, well, we can do something with that. We're going to write this down. We did not write this down on Friday, so everybody can write this down. I'm not going to write the grams times the meters because that's gross. We'll write the mass times the distance. So that's like my Y. What did you say my slope was? Got a slope of 1 times X. This is X plus B. Hopefully my B is 0. Okay. So this is mass. Oops, I guess that was 2 technically, given the way I wrote it down. Mass times distance for 2. So really what we're finding is that those products are actually equal. Yes, it should. I just had it, I programmed it in my brain to do it the other way, I guess. Thank you. If it was a 2, it would work out too, wouldn't it? Yeah, because it would just be by definition. So that's all well and good. Now, there's a little piece of physics that we've missed in this observation, and that is that it's not just the mass, but what's happening to that mass? Tell me about the forces acting on that mass. Pulling or pushing on it. Not a trick question. Don't overthink it. The earth or gravity is pulling on it, right? And then the stick is kind of pushing it up. So we've got, this is really not just the mass, but it's really a force there's a force pulling down the force of the Earth on, we'll call this one mass 2. And there's a force of the Earth on mass 1 over here. And it's really, does it make sense that if it's mass times distance, the force of the Earth is just going to be mg times distance? Okay, so really, instead of writing this, if we're going to do this in very rigorous physics terms, we would really want to call this the force times the distance. Oops, that should be a 2, is equal to the force times the distance. Okay. Go ahead, do you have a question? Are you sure? Because you totally can ask questions. Okay, if you do, let me know. So the force times the distance acting on one side has to be equal to the force times the distance acting on the other side. Okay? And this is where we get this funky word, torque. Okay? Torque. Torque is marked with the Greek letter tau. Okay? So if you know capital sigma, if you're familiar with capital sigma, it's right next to it, tau, right? And it's the little tau, even though we usually draw it kind of big. I don't know, it's just kind of the way the world goes. The torque of 2 has to equal the torque of 1. That's the game. That's the game. If they're not equal, let me back up. If they are equal, we can say that that system is in what? If it's not, we're not in equilibrium anymore in a situation like this, right? So now we're going to go back to Chris's weird, no judgment, but kind of, units of torque that he measured up here. So you said that on this side we had how much? What did you say? 15 key centimeters. Do you understand what he's saying there? There's a mass of 3 keys times a distance of 5 centimeters. So we've got a torque of 15 key centimeters on this side, okay, causing rotation on this side. Over here, you've only got 12 key centimeters, right, causing rotation on this side. This one wins. It's going to tip. Okay? Not in equilibrium. How are we doing so far? Are we okay? Okay. Yes, of course. I don't have to go quick. I can go slow. So this is going to lead us to a new definition of Newton's first law. Okay? When we first started doing Newton's first and second law, I always talked about them as the same thing, and now I'm not going to do that anymore because, you know, I feel a little more strongly about this in this way. So I'm going to go ahead and click. Is that okay? And we're going to write down Newton's first and second law. I'm going to write it down here. Everybody can write it with me. Newton's first law is really just the law of equilibrium. I asked you on, I don't remember what day was it, Wednesday maybe, or it was Thursday. I asked you what equilibrium meant. Remember that? What's that? And you told me when F net equals 0. Absolutely. You said F net equals 0. If F net equals 0, we know that the object is not accelerating. And then we're good to go. But then I told you the sad, sad story of, was it you, Josh? And TJ, you were trying to help him move a couch. It was a terrible, terrible situation where they were pushing against each other. Life was good. It was an equilibrium. And then one of them, I don't remember who's the smart aleck. Oh, Josh that took the step over? Yeah. So you took a step over. The net force was still 0, right? Because the force of TJ, the magnitude is equal to the force of Josh. One's pushing to the left, one's pushing to the right. But because Josh took a step to the side, it is no longer at equilibrium. So we need more than just this. In order to have a system that is completely at equilibrium, not only do you need F net to be 0, we also need the net torque to be 0. Okay. And torque, again, is defined as a force applied some distance away from a point of rotation. Okay? So it's a force applied some distance from an axis of rotation. It's funny because it takes until you get to junior or senior year of high school to actually hear this word, hear this concept, but you know this concept. You have learned this concept from the time that you were very small children, right? So let me give you an example of a time when you know that torque is a thing, okay? When you're a little kid and you start like really wanting to be like the big kid, right? And so you're trying to walk and you're trying to like hold the door for your dad while they're carrying groceries or something like that, right? So I'm looking at the door from above, and you know that you got to push on the door, right? Push really hard on the door, but you push right here. Is it going to be very easy to open the door? It is not going to be very easy to open the door. You push really push, and then your dad tells you to take a step over. Same force, right? Force of the 3-year-old pushing, pushing, pushing. But if you take a step over and push from here instead, with that same force that might not be that big, what happens? What happens to the door now? It opens, right? In fact, what happens is that the torque is not 0, and we can actually cause this thing to rotate. Okay? Torque gets bigger if you apply a bigger force, or if you increase the distance between the axis of rotation and the point at which the force is applied. Right? We utilize torque all the time in our daily lives, and you'll kind of see it if you look for it now. If you look for it, you can see that this is really true. Okay? Questions that you have on this right now before we keep cruising? So there's Newton's first law in all of its glory. Equilibrium is met if F net is 0 and torque net is 0. It means that the acceleration will be 0. And, oh, there's another one. What? There's another one. Yeah. I'm sorry. This little thing right here, does anybody know what letter that is? Don't say it's a fish, because it's not. It is alpha. Yeah. Anybody have an idea of what alpha might represent? That is not the one. That is true as well. Well, what does this A represent? Acceleration, linear acceleration, right? In a straight line, speeding up, slowing down. Yeah. What do you think? Rotational acceleration. That's exactly what it is. So what is rotational acceleration? You're like, I don't know. You're throwing all this kind of crazy stuff in my face, Miss Carbling. Rotational acceleration is this. If I let this thing go, the thing's going to fall. It's accelerating. It's not flying up or falling down, but it's accelerating in a circle. That's all it is. Okay? This acceleration thing here is rotational acceleration. How are we doing? We okay? Newton's first law, done and done. There is one more piece that helps kind of put all of this together. So I'm going to jump from one thing to another. It's kind of a goofy thing, and I apologize. I don't have any problems about this yet because we need one more piece of physics. Okay? And that one more piece of physics has to do with something called center of mass. Have you heard of center of mass before? Okay. So we're going to go ahead and you might want to just grab a new, like draw a line in your paper, or if you're ready for a new page, this is a great time to do it. Any idea what center of mass is? I've heard of it, but I don't know what it means. Chris, go ahead and say that for everybody, because that's what everybody's thinking. The center of all the mass, right? Y'all were thinking that. Yeah, the center of all the mass. So it's a location. Okay? It's the location at which all of the mass of an object can be, what do I want to say? I don't have it written down. Location at which all of the mass of an object can be located. Or not, that's not really what I mean. That's not what I want. I want to say. Identified for purposes of quantitative analysis. Huh? All right. I have a meter stick. Does the meter stick have mass? For sure it does. Where is all the mass located? All around, right? What's the word? Quantitative. It's poorly written. I apologize. There is mass over here, and there is mass over here, and there is mass over here. There's mass along this entire darn thing. If I cut part of it off, then some of the mass is gone, right? But if I want to look at this meter stick, I don't want to have to acknowledge that there is mass on each little piece of this if I'm trying to do a problem. I want to do a little bit of mass here, a little force of gravity here, a little force of gravity. Like, that's a lot of work. You know, on all the free body diagrams that we draw, we just draw it from a dot. You know what I'm talking about? Right? We have a box, we have a frog, we have a whatever, we draw from a dot. The dot represents this thing called the center of mass, right? It's where we can assume that all of the mass is, where all of it kind of cancels out to be, where if we throw that object travels, like the center of mass is the thing that travels that parabola. Where is the center of mass of my meter stick? Pretty darn close to the 50 centimeters, right? So I can take my fingers and I can find that spot, that place where if I only apply one force, it's going to balance. It's right around the 50, something right around there. There, oops, not quite, almost. So close, so close. So instead of taking this little piece of mass and this little piece and this little piece all the way down, I can assume that all of the mass, and it's not just the mass right here, but it's all of the mass, I can assume is at this very one point. That's what center of mass is all about. And we need to pay attention to where the center of mass is of an object in order to figure out what's going to happen with that object. I'm going to show you a couple really quick videos because they demonstrate this really, really nicely. Just can you do me a favor and turn off the front set of lights for me? These are just super quick for you to see what is going on. This first one is kind of, it's a little goofy, but I like it. Need to make sure that I've got sound for you. Just a second. Hey, there she is. All right. He has a couple of really nice demos, which is why I like it. Here we go. Oh, maybe. Go team.
We're going to be looking at several demonstrations that have to do with center of mass and how the position of the center of mass of an object is related to the object's stability. Let's begin with a parlor trick that you've probably seen before. Take a fork and a spoon.
Ways to impress your friends.
Interlock them. Slip a match in between the tines of the fork and balance it on a glass, or in this case, a beaker. And you can make the whole combination balance there. The reason that works is because the center of mass of the system of the fork and the spoon is actually right at the lip of the beaker where it's balanced. So the point of support is directly below the center of mass.
Okay, we're going to pause there for just a second. That's another thing you can write down about center of mass is that it's the place, if you didn't write this down already, that you can balance a system, okay? So I said that it was a place that you can say all of the mass is at, but it's also the place where if you apply a force just at that place, you can also balance the system. Sometimes center of mass is pretty obvious and makes sense in terms of where it is, right? Like the center of mass of my ruler is going to be inside my ruler right at the 50, right? The center of mass of my water bottle is going to be somewhere in here, right? At the kind of the middle of where the mass is. But in this case, the center of mass of this thing with this fork and a spoon, which have much more mass than the matchstick itself, right? But the center of mass is in the middle because of the way that those two objects are oriented.
The reason the center of mass is at that particular point, it's not actually within the fork or the spoon, it's somewhere here below it. Now, by symmetry, since the fork and the spoon are about the same shape, the center of mass is going to be along the line approximately here. But because the spoon extends way out and the fork extends way out, this will displace the center of mass downward. And so the center of mass of an object does not actually have to be physically within the object. Let's look at another example. Here we'll be using our two-dimensional NCSSM student. We'll call this 2D. And I'm going to put some weight on 2D's hands and balance 2D right there on the top of the head. It's very easy to balance. Now, like the fork and the spoon, we've got a lot of weight on the outside, extending out away from the point of support. Because of the symmetry of the object, the center, we know the center mass will fall on a vertical line right here, below my finger. And it's going to be quite a ways down because most of the weight is here on the clamps. Now, this is a very stable object. So I actually want to talk about why it is that this is stable and what the position of the center of mass has to do with that. I'll begin by looking at a different object where it might be a little bit easier to see what's going on. I'll just use this. This is a support for another piece of equipment. It has a wooden base and just a metal rod. Sitting like this, it's very stable. It's very hard to make this thing tip over. But if I put it like this, it's essentially impossible to keep it from tipping over. That has to do with what happens to the center of mass when the object tips. The center of mass of this object is inside the piece of wood. In order to tip the object, notice that the center of mass has to rise first. It's going to rise before it finally starts to fall over again. It has to rise quite a large distance. On the other hand, if the object is like this, the center of mass is now up here, and as the object starts to tip, the center of mass immediately begins going downward. So the difference is that if the center of mass has to be lifted, then the object is going to be more stable than if it just falls immediately. And the farther it has to be lifted, then the more stable the object will be.
That's worth writing down, right? And this is something that kind of relates to what we're doing in terms of stability. It's also just kind of good life lesson, and that is, again, that if the center of mass of an object has to be lifted in order to topple it, okay, it's going to be much more stable than if the center of mass can just fall. That kind of makes sense? Again, if you have to lift the center of mass in order to get something to topple over, that's a technical term, okay, then it's much more stable, much less likely to fall. It's okay. Can you tell us what's funny? I just am curious. All right, are we good? Keep cruising here.
Now let's take a look at 2D one more time. The center of mass of 2D is way down here because that's where most of the weight is. So I would actually have to pull this to the side like so in order to raise the center of mass. And in fact, I couldn't even raise the center of mass far enough in order to make the object tip over completely. On the other hand, if I put most of the mass above like this, now the center of mass of 2D will be up here, it will be above my finger. So as soon as I let go, the center of mass will fall immediately. And it would be impossible.
So does that make sense? Even though, I mean, it's the same mass, right? The object has exactly the same mass, but it all has to do with the distribution of that mass. And again, because the center of mass can just fall, it'll be really easy to get it to topple.
For me to balance without moving my finger, and even then it's very difficult. Now there are a number of toys that work on this principle. Here's one of them. This horseman has, the horseman is plastic, and there's a fairly heavy weight here on the end. So the center of mass is going to be down in here. Actually, the center of mass might be somewhere within the weight here on the end, or at least very near to it. We have no trouble balancing this on this platform. The center of mass is way down here below it. In order to make this thing tip over, we have to raise the center of mass above this point, and of course, that would be impossible without practically pushing it off of its stand. Here's another toy that works similarly. It's a bald-headed eagle, and this one can be balanced on its beak. Now, if you want to try this yourself and don't have toys like this at home, it's very simple. All you need is a pencil with an eraser and a paper clip. Open up the paper clip. Stick one end in the pencil eraser, and you can balance the other end on your finger. The center mass will fall on a straight line directly below my finger.
All right. So hopefully that was kind of helpful in terms of seeing what is going on. We're going to go do one really quick demo because it's kind of fun. We're going to go out in the hall real quick. So let's go quick. I'm going to say quick 5 more times. I know, this won't take very long. Talk about what's going on here. So, and I'll pass this around so you can see it. So it's pretty fun and it balances, but why? How does it do this? Because the center of mass is on my finger, right? I mean, that's what we learned from the video. My center of mass, or the center of mass of the eagle is on my finger. Why? You know, hold this and figure out what's going on. Not only are the wings so far out, but what do you feel in the wings? Do you feel anything? They're heavier here. Yep, and it's actually, if you, we had one of these at my house, and my daughters are little and break things. If you open this, and you can kind of feel it when you pass it around, there are actually weights up here in the wings. And so since there are weights in the wings, it's just like the fork and spoon, right? And so the center of mass is actually further up in the bird than it. If the weight was mostly in here, then the center of mass would be inside his belly, and then he wouldn't be able to balance on his beak. That kind of makes sense? So, yeah. So I'll pass it around because it's easier to kind of get a sense of it when you get to hold it. Be careful with him. He will break. I know this because I've, seen it. All right, I'm gonna show you one other really quick video. This one is shorter, but it's kind of nice, and this kind of ties together everything else that we've seen as well. So in the first few units that we did, when we were throwing things, when we were rolling things, when we were launching things, we just assumed, as we've said before, that everything was just a point, right? We just gonna draw things as a point. But the fun thing is that when you have things now with different distributions of mass, you get rotation that happens as well as motion. So this was done by the physics group at MIT, and some grad students asked to help out with this. So anyway, take a look at this. I'll stop it and redo it a couple times because it's kind of nice to see. Yep, so he's got like this, it looks kind of like a, I don't know, badminton racket or something, and that's like a mass on a, okay. Okay, so did you get the idea of what was happening there? So you could see the rotation of this thing as he was throwing it. You could see things flying backwards or forwards or whatever. There was all of that happening. But we're thinking way back to unit, I don't even know, 1 or 2 or whatever it was. We were doing projectile motion. So that's really what that is, right? It's just projectile motion. Take a look now. So what they did is they painted the center of mass orange, tossed the same light or the same objects under black lights. What do you see? So did you say it doesn't rotate? Does it rotate? It does rotate, But the thing that you see is just the center of mass, and the center of mass itself is just making an arc just like it normally would, right? So that's what we're talking about. We can assume that all of that mass, all of that matter is at one spot, okay? So if I took this meter stick and I threw it like this, which I won't do, but if I did, it would rotate like this. But as physicists that understand projectile motion, you would just watch the 50, and the 50 would make a nice parabola just like it would have any other time. The rotation itself has nothing to do with what the center of mass is doing. Okay, let's keep going. Watch them play, catch a little bit more here. Well, I think they're not really trying to catch it. Okay, so this disc, I think this is kind of cool. So this disc, that orange dot is the center of the object. Okay, so take a look at what's going to happen to the center of the object. Did you see that one? No? Did you see that it was kind of wobbly? Now, did you notice what they said? Oops. Did they say it was the center or the center of mass? It was the center. So watch carefully. So again, that orange dot is at the center of the object. This is the center of mass. Oh, it's loud. Let's go back and do that one again. Come back. Oh. Oop. So there's the center. Did you say whoop, 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 whoop? Here's the center of mass. Okay. How are we doing? You can get your test in just a minute. So I know they're so needy. What time do we? Oh yeah, we got time. We got time. That's perfect. All right.